Hello everyone, and welcome to this presentation today on the topic of modeling municipal and wastewater hydraulics using the CFD tool Flow3D. Any questions, do not hesitate please. Email me at john.wendelbo@flow3d.com. Of course I will be very happy to respond to any questions as best I can. I have a lot of materials for you today covering a broad range of topics, so I will be going quite fast. But don't worry, we will be emailing you a link to download the slides and the recording. Heads up though, I won't be spending much time on the nuts and bolts of how we set things up specifically within the Flow3D interface. Rather, what I hope to do is give you a really good sense of when and how CFD tools such as Flow3D can be useful for the engineer or the designer. So the focus will be on capabilities, on applicability, on usefulness, on real-life examples, those sorts of things. Municipal flows are very interesting because there's really quite a lot going on. It's usually complex. It's also eminently practical, and I would say highly consequential, since generally we are dealing with the built urban environment and or sensitive environmental considerations. So there's really a whole spectrum there of modeling interests. Some of the topics that go hand in hand with what I think of as the straight hydraulics part of the puzzle are sediment and grit transport, also sediment deposition and entrainment or re-entrainment, and air entrainment as well. And then also chemical or biochemical reactions and the way these couple with the hydraulics of a fluid. So that's how I've structured today's presentation. Okay, so traditional hydraulics, air entrainment, sediment processes, and then biohydrochemical processes. So this will include 3D transients, bubbles, grit, and all those things. Okay, so let's get cracking with the hydraulics. So first of all, it's important to understand where Flow3D operates. We live in the fully nonlinear world of 3D modeling. We live in the world of free surface problems, and this means of course that we also live in the world of transients. Not that we can't reduce problems to simpler 2D or 1D or shallow water equations if it's appropriate, or rigid lid approximation or what have you, not a problem, but our natural modeling strengths are in the free surface 3D transient modeling space. So that's important to understand. And built on this core modeling platform are numerous models which integrate to address a whole range of water and environmental modeling situations. This slide just reiterates this and maybe also conveys some key notions. One is versatility, and I think other reasonable key points would be speed, ease of use, and accuracy. So I presume everyone knows this, but it doesn't hurt to dot the I's and show what the solution of a transient 3D solution of a free surface problem looks like. You can see the detail of the jet, of course, but also very interestingly the low frequency flapping of the central nape. Okay, this oscillates back left and right at a much lower frequency. Okay, so that is the transient of a duct outflow, and everyone knows about tanks and vertical pipes. So what you will see here is the formation of an aerated vortex core following the kind of initial choking transients we are familiar with. The flow is coming in the tank from the top left corner, and which is why the drainage eventually settles into a vortex type core. All right. So moving more closely to municipal related topics, wet tunnels. Oh, I guess we've reached our maximum there. So moving to more closely municipal topics, wet tunnels, storage or diversion tanks, CSO structures, hydraulic controls, sluice gates, drop shafts. Usually all of this becomes critically important in the context of wet weather surges. We might have a problem here because this is coming up over and over. Hopefully not too often, not too disruptive. Okay, so it is disruptive. Let me see. So what I want to show here is that what's important in these conditions is that we will the system will move from free surface conditions to being pressurized and then back to free surfaces and so on. So it can get complicated, and it helps to be able to visualize how all these conditions might fit together. So to illustrate this, what I have here is an arrangement of tanks and pipes, and then these gates are able to move up and down. So the flow is being pressurized through this inlet on the left, and then the tank will fill up. And then the first gate we are going to open is this one here. And so you'll see a pretty rapid discharge through this pipe, and then some complex behaviors as this tank fills up, and we have other pipe relations. So this is going to open in a minute. And we'll see the transitions that can occur. So this continues to be pressurized, this opens, this obviously oscillates up and down a little bit, this tank gets filled up, and we have, interestingly here in the outlet pipe, we are not really using these we are not using the full potential of this of these pipes here. So meanwhile, also what happened is that this gate opened up. So I can play this again. We can take a look. So we see also some aeration here and some aeration right here. This isn't really filling up completely. So these are the sorts of things we can see by modeling transients and mixed pressurized conditions. Now, in reality, pipes between reservoirs might be quite long, kilometers sometimes. So in Flow3D, instead of modeling the whole extent of the pipe, we take a shortcut and simply add what's called a baffle, porous baffle element, which in effect creates a porous element, but which has a drag coefficient, so that we can assign a pressure loss across the section. So what you'll see is some pipes filling in from the left here, from these two. And then what we see here is where the baffle is located. It's kind of an imaginary component. We are observing a head loss, which would be equivalent to having a much longer pipe. And once this gets fully pressurized, what you'll see is that even in the pressurized condition, we still have the head loss across the baffle. So that's how we go about modeling those types of things. And then another example, in this case we are modeling an energy dissipation structure, and again an example of free surface hydraulics. Okay. Now finally, this is a real case up in Illinois, I believe. It's a CSO structure, so something that is already built, but is under consideration for retrofitting. So the engineers needed to get a full understanding of the behavior of the structure under various pressurized upstream conditions and gate openings. So the wastewater comes in from the left, and there's an interceptor tank here, and then the flow can go over this opening here, and in fact we can't see it, falls into a culvert. So I have a little video of the structure. Maybe this will help a little bit. We have the main tank and the interceptor and then the gate here, and then this hole here gives into the drain, gives into a culvert underneath, which isn't modeled here. So when we actually model this, you're going to see the water getting pressurized from the inlet on this side, and then we can see what's happening as the pressure increases. And so in this case, the reality of this structure is that the fluid, the tunnel got fully pressurized, and so we wanted to see how these things would work out. So you have the pressurized tunnel here on the right, and then filling up, and with the overflow going down into this culverts over here. Okay, play that again. Okay, and then we can also make this gate move up and down, of course. So one of the very simple things to do in Flow3D is to include traces in the simulation. So you can visualize things very easily, and also look at the key outputs such as residence time or hydraulic efficiency, and you can also include some chemistry in the mix, which I will get to a little later. So in this first example, we just have the fluid coming out here, and if I play this back from the beginning, you can see that it's a fairly inefficient way of mixing things. But with the help of traces, we can really see where the fluid is going and what's happening. In this lower case here, which I'm going to play in a second, we've added some internal baffles, and so what you'll see is a much more robust mixing process. And so with the use of traces, you can test different alternatives, design alternatives very easily, especially since in Flow3D we don't really remesh things. We have a kind of a fixed mesh method of representing geometries. So you just add this geometry, the inner baffles, and then just proceed with the simulation. Okay, and then we also have a general moving objects, which can be very useful in certain applications. This is a volume rendering you're seeing. Not much to elaborate, except that resolving the detail of the mixing blades can be in fact quite demanding computationally. So for these situations we also have an alternative in Flow3D, which is what we call fan objects, and these impart both vorticity and momentum to the flow, and it's an alternative efficient way of looking at these types of mixing problems. Okay, volume rendering simply shows you where certain concentrations are found in the flow. We have some streamlines and all those nice things. All right. In practice, of course, now and then we get to see some interesting write-ups from our users, so it's always nice to see how the software is used in practice. So I'll leave these here for reference in the slides. And I added this slide to underscore the fact that in fact we transition very smoothly from the type of hydraulics I've just mentioned to larger scales and what I think of as water and environmental problems, river hydraulics, thermal plumes, hydraulic zones of influence, contaminant transports, and so on. It's not really strictly the municipal category, but many companies work in fact in both contexts, municipal and environmental, and so it's useful to know this. Okay, to sum up this section, in terms of hydraulic modeling, Flow3D is definitely a very versatile tool that performs well on many applications and just can help in all sorts of ways, from design to remediation, retrofit, and so on. That's really my take-home message on that front. Okay, so so much for hydraulics, and other things matter as well. Air entrainment can be a major headache. It can also be a very expensive headache, and so that's something we need to pay attention to. And one of the case studies I'll show you in this section is is this flume. This is a flume which gives into a tank. It's an effluent. There's a tank, and then these tanks have some vertical pipes which will then go underground, travel a few hundred meters, and then rise up again to a weir type structures. And the problem we're having, I'll get back to this shortly, is that the bulking in the pipes is preventing the flume from working. In fact, the tank starts filling up. This is, I guess, time 2. Tank starts filling up, and in fact there's a reverse flow back into the flume, and then it's completely flooded, and the whole thing becomes completely inoperational. So we'll get to that very shortly, but what tools do we have for air entrainment? We have one option is to resolve the bubble itself. That's for large bubbles, pockets of air. So we have an adiabatic bubble model which resolves just the whole thing. And then we have a parametrized solution, which is called the air entrainment model, and which uses near-surface turbulence and what's called the drift flux model. And what we evaluate, rather than the single individual bubbles, is the air fraction, the total air fraction within a fluid cell. So this is a very fast and very economical solution, but it's also a very good solution for many cases. And then when you need extreme kind of detail, we have a two-fluid solution where you not only resolve the water side of things, but you fully resolve the air side of things. And so I'll show you these how this works. So this is the resolution of the bubbles themselves. It's the adiabatic bubble model we have. There's a full resolution, and what you can see, this is in fact this is from a project in New York. Upstate New York, where we have the aqueducts going down through the Catskills to New York City, and on the way, so this is the aqueduct, and on the way we have these pumps which siphon water out of the aqueduct to the small towns on the way down. And the problem they're having is that in certain conditions they're getting very strong cavitation in their pumps. And so in this case we're able to resolve the actual bubbles, because they're so large, coming out of the fluid as the fluid is being sucked up into the pumps. So the fluid is moving left to right. You can see some vortex shedding here and some interesting behaviors, but that's a kind of a different story. And the bubble entrainment up the shaft here. Next one is same thing, but we have a drop shaft here. It's actually a tangential drop shaft, and we have an event where water is being dumped into a larger pipe. And we have two things here. We have the water phase here, and basically the water is coming in, kind of circulates down tangentially down this drop shaft, and you can see this. Let me play this again. There you go. So if I pause it here, you can see the fluid coming in and then circulating, and then we have the aerated core. Now, so this is the motion of the water, and you can see the splash and the resulting wave. And this is the air side, but on the air side we are just resolving for just the air pressure as a bulk quantity, no detail. But we still get a very good feel for what's going on. So we have this influx of water, which eventually is going to stop, and we'll see the flow dwindle down, and we have a wave propagating left and right as we would expect, and a ton of air entrainment here, and then eventually this stops. Okay, so that's the adiabatic bubble model. Now, if we want to resolve both sides, not just the water but also the air side, we can use a two-fluid model, and then you see a very different, well, not very different, but you see much more detail about what's happening with the air side. We have a ton of like underwater bubbles circulating, and we have the same front moving left and right, but now we're fully resolving what's going on the air side, and you can see this is in fact what we're seeing up here is the aerated core. This is the center of the shaft where there's air. Okay, so those are options we have, and then we have the air entrainment model, which is the kind of scalar model, the how much air do we have as an average in a fraction of air inside a computational cell. And there's a tech note on this, and if you download the slides you'll be able to take a look at this link. It's also on the website, which gives you the full detail of what's happening, how this model is built. So going back to the case study, we had an open channel effluent flume here. The flume is there. We have a first channel, a flume, a second channel, and then a tank, and then the water goes down the pipe all the way and up again to a weir. Okay, and the problem is, so this is about 20 meters drop, then about 300 meters long. And we're having these two major problems. One is the water level oscillation, which is making the flume inoperable. And we're also getting these explosive bubbles at the exit here. So this oscillation is about 90 seconds. It goes up and down at a pretty fast pace, every 90 seconds period. The explosive bubbles happen about every 20 minutes. Okay, so let's keep that in mind. So here, detail again, we have the flow coming in, going down, and then coming up again over this weir. Okay, so water comes in, raises, the water bulks basically because of all the air entrainment, rises some more, reverse flow, and then on the other side, on the weir, we see this explosion, I guess, of air every 20 minutes. Okay, and then it goes back to normal and things continue. So we model this simply using a straight hydraulics model and then turning on the air entrainment model because that's the most appropriate model for this particular situation, and just kept the defaults and see what happens. So it's kind of amazing actually when you think about it, but we run the model and we observed exactly what was observed in real life, which is this oscillation in the tank here with the reverse flow onto the flume. And the period here is actually about 80 seconds, very close to 90 seconds that it was observed, and then we have this pressure wave coming up on the outlet. So the whole model was the whole system was modeled, and we observed exactly what was observed in real life. So this served as a basic validation for our model before we explored other remedial options. So just seeing things as a 2D slice, you can see the water oscillating up and down, and the bulking. So the of course, when air gets entrained into the water, the density is reduced, and that's why you get these oscillations, because the density is varying with time and oscillating with the rest of the system. Okay. So as I mentioned, so this is the surface elevation at the first tank. Goes up and down, about 2 meters, which is what was observed, and in fact the high water line was also accurately at 1475 meters elevation was also accurately predicted. The period was 80 seconds. In real life it was about 90 seconds, but that's already pretty good. And then I confess I wouldn't have run this as long had I not known about this, but lo and behold, around 1500 seconds, which is about 20 minutes or so, we did in fact observe this spike in kinetic energy in the whole system as we had this explosive release of entrapped air, which is accompanied by a large release of air in the whole system as a whole. So so far this is an ongoing project, so excellent validation of the model. We have the upstream tank oscillation period, we have the downstream burp, we have the amplitude of the phenomena that is being correctly captured, and it's nice that we have the high elevation watermark to work with. And now we can use Flow3D to explore, we've already done this, but I'm not reporting it here, where we explore many designs and solutions to remedy this problem. You know, there is a challenge that in fact the design as built has a very strong sensitivity to any kind of bulking. Very narrow margins of operation, so it's going to be a challenge to fix this, but the beauty of Flow3D or any CFD code is that you can explore many design solutions to narrow the options. Okay, so if anyone's going to be at WEFTEC in 2015 next September, we should have an interesting update for you then. Okay, so another example, this was presented by Ryan Edison from AECOM a couple of years ago. Really nice drop shaft, tangential drop shaft study, and I'll kind of browse through this. There's an inlet channel, a drop shaft, and then a deaeration chamber, an air vent, recirculation, etc. And this was a large, massive project actually in Indiana. Indianapolis, and the idea here was to design things using CFD ahead of time and then use physical modeling as a final validation, but not to use the physical modeling in the design phase. And in fact, Ryan was so successful with his CFD-driven design that the comment when they built this in the lab at IIRH was, I'll read it, we took that design to Iowa and built it based on CFD, and it worked perfectly. The staff told us that this is the first time they've actually just set something up and it just worked. They said they didn't have anything to change, so really great kind of validation for the beauty of using CFD methods ahead of the physical investigation. Okay, so this was a really nice success, and what this looks like as a kind of CFD, there's a transient here, this needs to fill up a little bit, but as a CFD model, in fact, if you have a drop shaft here, and if you look at the top, you see the aerated core very well and the streamlines. These are actually quite straightforward models to create in Flow3D. Okay, so I would say that the cost of running an air entrainment model within Flow3D is actually minimal because it's a very efficient, computationally efficient model, and so there's no reason really not to run that. When you have a situation where you anticipate that there could be some problems, definitely just you just turn the module on, and this will give you some good insights as to if there's any danger. Now there's other situations, maybe more involved, where you want to resolve more detail. So in that case, you can use kind of fully resolved free surface calculations we do. And it's very rare, but sometimes you need the air side of things as well. And in that case, that option is also available, although the cost computationally is significant. But it's doable. So sediment processes. Extremely interesting, very important, and we're talking about grits, particles, sand, and so what we rewrote pretty much everything for Flow3D V11, which came out last summer, I think, and so we really have a nice tool now, which allows you to look at a lot of different things in a very practical, functional way. Some of the key elements are that we define multi-species, so a whole range of grain sizes if needed, and we do so the transport of suspended material, that's what we use a drift flux model for that, but we also now have deposition, so when the particles reach a solid surface and depose and stop moving, the ensuing packing, and then on a packed, erosion on a packed surface, there's entrainment or re-entrainment, and then slope adjustment and bed load transport, those sorts of things. So it's become a really powerful model in Flow3D. And a first case was also by Ryan Edison from AECOM, and this was an underperforming vortex grit chamber. This is a presentation he gave last fall in Toronto at a user conference, and the problem here was that the chamber was just underperforming, badly underperforming, and so what could be done? So this is a kind of a remedial situation. Let me go back maybe. So we have the influence, circulates around, goes out this way, and then the hopper down here to capture the coarse grit. Okay, these are some pictures. It's a pretty big structure, 24 feet diameter. And a bunch of internal structures here, and no one's too sure about what does what, so CFD can help with that. And with built structures, the nice thing is that you can validate your basic model, just like we did with the air entrainment problem I just showed you. We can validate the model with what you actually have, and then work sort of design parameter space to find good solutions. And so the first validation shows that Flow3D accurately, first of all, predicts the hydraulic jump, which we do very well anyway, so we sort of knew that, but also the areas of high turbulence. So that was nice. So then what Ryan did was to say, well, what are our options in terms of simple designs here to try and fix this problem? And he did a coarse resolution, but a parametric study, a very systematic parametric study, coarse resolution, and just narrowed just to see what effects changing things around would have. And so he compiled this table and came up with recommended changes, which would not cost very much at all, and had the highest likelihood of fixing or improving the performance of the grid chamber. So the three recommendations were to remove one of the baffles, internal baffles, to remove the propeller, which was not helping, and to remove the grid hopper cover plate. When they did this, the coarse grid removal went up from 77% up to 99 to 94%. So, and the target was 95. So, pretty much mission accomplished. And with, in terms of fabrication or refitting, a very minimal cost. Okay, so in Flow3D, this is a kind of a snapshot of the screen. We can specify any number of species, so you can have a composition of very coarse millimeter type particles, and then down to 10 microns. 100 microns, I'm sorry, 100, 300, 500 microns. And we just basically and give densities to all these different particles, so they don't all have to be the same. This just happens to be sand type materials. Drag coefficients, maybe close to 1 usually for solids. And then a couple more coefficients. Mostly the defaults are pretty robust. And so what we model then is the transport, as I already mentioned, and then the deposition, re-entrainment, and those sorts of things. Again, this has been used nicely in the industry. And I'll give you kind of a example here of something very, not the same, but similar to what Ryan had worked with. This is a slightly different design, which kind of forces the influence. Let me see. So the water comes in here. Is forced downwards and then spirals. So there's no propeller in this, no impeller in this design. It's forced downwards and then circulates a little bit and then comes back through the middle into the outflow of the structure. And what we are looking at here is different packed sediment distributions for suspended. The distributions for different sizes. So we have 100 microns, 300 microns, and up to millimeter. And what we see here, these are 2D slices. I'll maybe just play this once again. What you see is the water coming in, swirling around. You can see the streamlines a little bit, and then going up here. So this is a view of the suspended particles, all of them, and this is a view of the packed sediment. So we see that the sediment, by and large, is packing on the this section of the structure and at the bottom, of course. And then in the sediment case, we have not too much suspended. Sorry, in the suspended case, we don't have too much suspension here. It's all happening here. Now we can refine this by particle size. So at 100 microns, we have an awful lot of suspended particles. Okay, and conversely, at the very coarse materials, almost no or much less suspended particles, and that's because they are not suspended anymore. They have touched the walls of the device. So another way to look at this is volume rendering, and so I'll play this one. Same thing, streamlines, and this is volume rendering of the packed sediment fractions. So where is the sediment packing? This is the very coarse grit, and this is there's plenty of grit that is holding on to the side walls and here to the bottom of the well. If we look at the next size down, 500 microns, there's still plenty, but it's yellow and green instead of red and yellow. So there's less of it, but still plenty of packed sediment. And then 300, still plenty, but less. And then the very finest particles at 100 micron, almost no packing. So that means that the coarse particles, let's say 300 to 1,000, are mostly, in fact, indeed getting packed onto the structured surfaces, and then they'll make their way down, whereas the finer ones are, in fact, being almost entirely entrained. So those are the insights you can get from this kind of modeling. What sizes go where, what speed, how do they pack, what's entrained, etc. So it's very useful for grit removal and clarifier applications. You can look at things by particle size. You can look at things with how they pack and sediment, and there's plenty of versatility to change geometric design with usually actually no change in meshing because of the way we mesh things. So it's a really good tool to run, again, the design parameter space. Now in a sediment clarifier structure, finer particles. And so what we see here, in fact, what we have is water coming out through this central pipe and then being pushed down again and then making its way over a weir, and the outflow is here. Okay, and these are 2D slices of the suspended particle concentrations. So you can see that at 50 microns, the water up here is really quite clear. Most of it is drifting down to the lower parts of the clarifier. At coarser particles, 100 microns, these are inverted actually. This is the 100 and this is the 50 and this is the 20. So at 20 microns we see in fact that most of the stuff is being entrained and goes straight to the output. And so not surprisingly what we see is this is kind of the 1 minus the removal percentage. So the very coarse particles, if you look at the outlet, nothing's making it to the outlet. So it's removing all of the coarse particles, and it's removing about 90% of the 100 micron particles. For the finer ones, it's not doing a very good job at all. We're around 70% for the 50 and barely 50% for the 20. So at this given flow rate, not too good. But it's good to know that before you build it, of course. You can test all these things way ahead of time. So switching gears a little bit, still sediments, but we can look at impoundments. Kind of interesting problems because we have usually environmentally sensitive things, but really the practical side of things is we put all this water which is laden with a lot of sediment into a pond, and where do things settle? This is the first example. We have water coming in here with a bunch of sediments, different sizes of grain size. And what we are seeing here, these are really the hydraulics. So okay, there's a circulation and then a secondary area of recirculation. And I'll pause this. What we are seeing in the top left here is actually the buildup of sediment. So the water is kind of transparent, and what we see here is the buildup of this sediment, where you can see that we're having some sediments building up in this top left corner, and this is a top view. So with this configuration, this is what's going to happen if you dump this fluid into this basin here for a long time. And let's see, so the sediment is going to accumulate here. It's also going to accumulate here, and we can see the actual buildup on this frame, and so on. So we can see where things are going to land using this model. And this is a slightly different sequence, where many more particles in this case. So we see faster filling up, plenty of accumulation of sediment here, and then in fact this is a pump, and so we are going to, there's a sequence here where we are adding water, and then there's too much water, so we're going to turn the pump on. It's going to remove water, and the water level is going to go down again. And I just let this run to the end, so the water is being pumped out from here. And so this is the top view of where the sediment has accumulated. This is a perspective view, and as the water comes down, you'll see that we will in fact see where the sediment has accumulated, and then we're left, there's no more water to suck out, so we are left with these ponds. Yeah, so that's pretty interesting. And so sediment loads and particle sizes and concentrations and flow rates and pump locations and general operations all, of course, significantly affect the distribution of packed sediment. So get some good insights from running these simulations. Now, going a step beyond, when fluids are laden with particles and flocculants and so on, depending on the size and concentration, the fluid may acquire non-Newtonian behaviors. So we also have advanced modeling options for these types of fluids. We have a specific module for granular flows, and we have non-Newtonian flows as well. So the models are excellent given that we have rheology data from field measurements. You need, it's just too complex to try and guess based on particle composition what's going to happen. So you need rheology data from field measurements, and then once you have that, you can do some curve fitting and build proper constitutive relations for the fluid. So two general mechanisms we observe. One is shear thickening, which is generally for the coarser granular type flows, slurries, and then we also have very often for the smaller, finer muds, we have shear thinning rheological behaviors, and so we handle both. We have even another layer of sophistication with elasto-viscoplasticity. So I'm just putting this here for reference. It's a pretty specialized topic, but it's used. It's currently being used by Flow3D users for complex tailing floods. So the granular flow model is kind of separate, and that's appropriate for shear thickening stress-strain relations, and that's actually quite a simple model to use in the scheme of things. And there's a tech note here which I'll leave for reference in the slides. So this is a little example of a granular flow model. It's a dam break, but this is a slurry. And so what you'll see is that in fact after a while, because of the mechanics of granular flows, instead of just spilling out forever like a shear thinning or a fluid, a water dam break would happen, in this case the breach stops on its own accord after a while. Instead of the whole thing spilling out, we get some spillage and then it stops. And that's a mechanism that's very specific to shear thickening granular media. And then you can see where the sediment in fact has accumulated downstream, which is kind of what you would expect given this geometry. So very interesting. And then I have a few minutes left, so I'm going to go to the biochemical sides of things. We have standard models in Flow3D which are, well, they're okay, but they are limited. We resolve first, second, and first and second linear systems. So we can have up to 99 species, and this is really the model equation that we have in our chemical model. A few other things we can do are phase change, evaporation, residue, and that's really a different model, the phase change model. And then for nonlinear reaction, what we have are entry points in the software for users to write their own customization. And that's been done, and I'll show you a little bit of that. But first, has an interesting problem, it's bitumen. So when it leaks, there's the naphtha that's contained in it flashes with the air. And so it leaves the liquid, the medium, and what results is that bitumen over time becomes denser and more viscous. And that's due to a chemical reaction as the naphtha flashes out of the fluid. So that is something we modeled with the chemical model. And so here we have a leak of bitumen. And what you can see here is that as time progresses, okay, so this is going down the canyon, I'll pause it, as time progresses, the density of the furthest reach is going up. We have a density lower here, and then the viscosity is also going up as time progresses. Okay, so these are the behaviors you can capture with the chemical model. Okay, and looking at this, it's similar but different case. This is also bitumen, and you can see the density increasing as the naphtha basically flashes out of the model of the fluid. So you can see that in this case we can actually approximate how much time it takes for all of the naphtha to leave the bitumen, and then at some point it reaches the riverbed, and there's no water in this case, but this would be when we would reach an environmentally critical point in time. Okay, so those are some things we can do. And then for the non-linear case, we have some work that was done by Cecilia Milan and the co-workers, I think a year ago, maybe 2 years ago, yeah, 2013. And so she wrote her own customizations to allow her to model bidimensional coupling, so in a nonlinear fashion. So these are nonlinear equations, and she was able to plug that in. So she got a solution for this, plugged it into Flow3D, and combined basically the hydraulics with the chemical. And so she was able to look at a man-made pond, and she specified a pumping rule for the two scalars, and then was able to look at oxygen contours and organic carbon and so on. So this is, I'm going over this very briefly because it's a new topic for us, and I think for many users, but it's definitely something a lot of people are asking about this, and so it's something that I anticipate where we are going to be working more on this in this field in the near future. Okay, so thank you, and to download the slides, or if you have any questions, email me. In fact, we'll be sending you a link to download this presentation, but any questions, just email me at john.wendelbo@flow3d.com. Thank you again for attending.